Right, good morning. Oh, it's afternoon. Oh, good afternoon. It's already afternoon. All right, today we're going to start with chapter 16, the oscillator. All right, all these oscillators basically feedback oscillators. All right. In this case, we're going to make use of positive feedback. All right. We will get basically two types. We'll get RC oscillators and we'll get LC oscillators. All right. But all of those oscillators got positive feedback. All right. What does an oscillator do? The oscillator will have a DC supply, will have electronic circuitry, all right, and it can give you a sine wave, a square wave, and a triangular wave, all right, or a sawtooth wave. But that's what the oscillator do. It will oscillate, it will give us an output with a DC supply. Now let's go and talk about the feedback oscillators. What is going to be the conditions? As I already mentioned, what do we have? We've got an amplifier with a DC supply. We've got a feedback circuit. What is in the feedback circuit? Attenuation and phase shift. All right. Depending on what is the phase shift across the amplifier will depend about my phase shift. But it will be positive feedback. All right. You with me? All right, if we have a look at this first figure here, you can see there's the input and the output of the amplifier in phase. There's no phase shift between my input and my output. That means across my feedback circuit, there isn't also no phase shift, all right? If I don't have any phase shift, then it will be positive feedback, all right? In this case, if you look at this amplifier there, what is the phase shift between the input and the output? 180 degrees, all right? That means across my feedback circuit, I must also have 180 degrees. That means 180 and 180 will give me 360. That means it will be in phase. It will be positive feedback, all right? Any questions? All right, the next part is the conditions for oscillation. What must the conditions be? All right. First of all, the phase shift around the loop should be equal to 0 degrees. All right. The phase shift around the loop should be equal to 0 degrees. That means that will give me positive feedback. And then the closed loop gain will be the gain of the amplifier times my attenuation. B stands for my attenuation should be equal to 1. I repeat. The gain of the amplifier times my attenuation should be equal to 1. The closed loop gain should be equal to 1. Not the gain should be equal to, the closed loop gain should be equal to 1. That means the gain of the amplifier multiplied by the attenuation should give me 1. All right. That's the two conditions. 0 phase shift, or the phase shift around the loop should be 0, and the closed loop gain should be equal to 1. That is the two conditions for oscillation. Any questions? Not yet. All right, let's move on. All right, starting up conditions. If I want to start up the oscillation, I want a gain to be a little bit larger than 1. You see here, they say the closed loop gain should be larger than 1. That is just for starting up, all right? When it starts oscillations, I want my gain to be my closed loop gain to be equal to 1, all right? Because if you make the gain too high, what will happen? It won't give me a sine wave, it will drive it into saturation, all right? That means these top edges will be cut off if my gain is too high. If you build a circuit like that and it clip off on the top hand side, that means then your gain is too high, then your gain will be larger than 1. If I leave my gain larger than 1, it will basically saturate, all right? Right, 16.3. Oscillators with RC feedback circuits. All right. As I already mentioned, we get RC oscillators and we got LC oscillators. The first one we're going to talk about is going to be our RC oscillators. The first one is the wind bridge oscillator. That is a RC oscillator. Now the feedback circuit of this wind bridge oscillator is a lead lag circuit. All right, the lead lag circuit, it's a RC circuit. We've got a series parallel RC circuit, and the response of that will be basically a band pass response. You can see the response of that will be give me a band pass response. And the center I will have my resonant frequency, and then you can see that the output is basically 1/3 of my input. All right. I repeat, the output is basically 1/3 of my input. All right. That means that's the amount of attenuation. If we look at equation 16.1, V out over V in is equal to 1/3. The formula for my resonant frequency, 1/2 pi RC. All right. That is my of the lead lag circuit. All right. That means my attenuation is going to be 1/3. What will the gain of the amplifier be? To get a closed loop gain of 1. It should be 3. When I got a gain of 3 of my amplifier, that means then my closed loop gain is going to be equal to 1. Let's have a look at the basic circuit of a wind bridge oscillator. If you look at this amplifier here, you can see where's my input? My input is here. What type of amplifier is that? If you have to name that amplifier, what type of amplifier is that? Anybody? It's a non-inverting amplifier. That means my input and my output is in phase, all right? And here's my lead lag circuit. Now, if we're going to look at this circuit, there's R1 and R2, my voltage divider. Here's my lead lag circuit. If I redraw that circuit, I can get that. That's why they call it a wind bridge oscillator. This is basically a bridge connection, all right? There's R1, R2. Let me just show you how do we get that. If you look at R2, it's connected to my reference. R2 is connected to my reference. The in between R1 and R2 is connected to my inverting input, all right? The top of R1 is connected where? To my output, all right? Now let's consider this lead lag circuit. R4, the top of R4 is connected where? To my output. The top of R4 is connected to my output. Then I get my capacitor. The capacitor and this resistor and capacitor tops are connected to my non-inverting input. You see there, it's connected to my non-inverting input. And then the bottom of C2 and R3 is connected to my reference.
So sir, in the test, like if you ask to draw the wind bridge, you can draw either one.
Yeah, you can draw any one. I just want to show you why they call it a wing bridge, because that is a bridge connection. There's the one leg and there's the other leg, and how they've been connected. That means this circuit and that circuit is basically identical, just different drawn, all right? There's no difference between those two circuits, all right? You agree? All right, here again they give us the closed loop gain of a non-inverting amplifier. You know that formula. The closed loop gain is equal to 1 upon my attenuation is 1 upon R2 divided by R1 plus R2, or it's equal to R1 plus R2 divided by R2. All right. That's the formula for the gain of a non-inverting amplifier. All right, first of all, they say the phase shift around the loop should be equal to 0 degrees. There's the feedback circuit drawn. The positive feedback loop, phase shift should be equal to 0 degrees. And here they say the loop gain is equal to 3 times the third is equal to 1. That means the gain of my amplifier should be equal to 3. 3 times the third will give me 1. All right, there they just work it out to tell you that the gain of the amplifier should be equal to 3. Right. The gain of the amplifier should be equal to 3. Now again, we need startup conditions. Now what have I told you about starting up? What should my gain be for starting up? For starting up, what should my gain be? The closed loop gain should be larger than 1 for starting up conditions. And that brings us to the following. If you look at this circuit here, not very practical. They say the loop gain should be larger than 1. That means if you make R2 variable, I can increase my gain. That's for starting up. And when it's oscillating, I can decrease the gain a little bit to make sure my loop gain is equal to 1. But that's not very practical to go and sit there with a variable resistor to do that. All right? You with me? Yes. Now there's certain things we can do to do that. The first circuit is the circuit with two Zenodiodes back to back in that circuit. Now, what will happen in this circuit? We know the Zener will conduct when the voltage go over a certain value, all right? Now, when I switch on the power, what will happen? Those two Zenodiodes, will it act like an open circuit or short circuit? Because we're starting up, the circuit must start oscillating. Will those Zeners look open circuit or closed circuit? It will look open circuit, all right. That means what will determine my gain? My gain will be determined by R1 plus R3 divided by R2 plus 1, all right. You with me? That will determine my gain. That means now I will have a gain larger than 1, and it will start oscillating. When it starts oscillating and the voltage go over a certain value, the Zenodiode voltage plus 0,7, when it goes over that, what will happen? It will start conducting, all right. That means the one Zenodiode will be reverse biased, the other one will be forward biased. Doing what? Basically sort out R3, all right. Now what will determine my gain then? Only R1 and R2, all right. You with me? That means now my gain will decrease to 1. Exactly 1, or the closed loop gain should be equal to 1. You with me? Must I repeat again? When we start off, Zenodiodes will look like open circuit. The gain will be determined by R1 plus R3 divided by R2 plus 1. If we go and look at the complete formula, now that should give me a gain larger than 1, all right, for starting up. When it oscillates, when it starts up, and the voltage is large enough, then the one Zenodiode will be forward biased, the other reverse biased. That means that will short out basically R3, and now the gain will be determined by R1 divided by R2 plus 1. And that should be equal to closed loop gain of 1. All right. Any questions?
Sorry.
Yeah.
Can I ask? This is just a general question, sir. What happens if there was only one Zenodiode?
All right. There's a question. If there was only one Zenodiode, what does my signal do? It goes positive and then through 0, negative. All right. That means if there's only one, it will only work for one cycle, not for the other cycle. Because if the output is positive, that Zenodiode will be reverse bias and that one will be forward bias. For the negative cycle, this one will be forward bias and that one will be reverse biased. All right. That's why we use two Zenodiodes. Right, the next circuit. A little bit more complicated circuit, but a much better circuit for the self-starting wing bridge oscillator. In this case, we got, what do we call that? What do we call that? What will we name that component? A junction field effect transistor, a JFET. All right. Now I hope everybody in this class knows the operation of a JFET. I'm going to ask a few questions to check if you know the operation of a JFET, because that was done in electronics too. Is that right? All right. If I put 0 volts on the gate of the N-channel JFET, what will my current be? Will I have any current, no current, or what current will flow if I put 0 volts on the gate of the JFET? All right, let's start where? Always ladies first, eh? What are you saying? I don't know, sir. What are you saying? Huh? What is that maximum current called? Not IG, you're talking nonsense. What are you saying? IDSS. IDSS is the maximum current. IDSS. That means if I put 0 volts on the gate, then I will have IDSS. Is that a voltage amplifier or a current amplifier? Is a JFET a voltage amplifier or a current amplifier? What are you saying?
Current.
Current. Do you agree with him? Yes, you agree. Do you agree with him? Do you agree with him? You don't know. What are you saying? The current amplifier. Unfortunately, all of you are wrong. It's a voltage amplifier. A bipolar junction transistor is a current amplifier because you use beta. What is beta? IC divided by IB. Here you use GM, the transfer conductance. That means this is not a current amplifier, it's a voltage amplifier. Why? Because we apply a voltage. What does the voltage do? It varies the depletion area. By varying the depletion area, it varies the flow between the drain and the source. All right. That is a voltage amplifier. All right. You with me? Now what happens here? If I switch on, this thing will automatically control the gain. All right. When I switch on, the voltage here will be basically 0. When it's 0, there will be a current flow. All right. And when the output will start increasing, when it decreases, creating a negative cycle, this diode will be forward biased during my negative cycle. That means it will charge this capacitor negative, positive. All right. You with me? Now, when I apply a negative voltage on the gate of the JFET, what will happen? It will decrease my drain source current. And by decreasing the drain source current, I will control the gain. All right? And that's how this circuit works. But first of all, you should know the operation of the JFET, and you should know what happens here. As I already mentioned, this diode will only conduct during the negative cycle, because during the positive cycle, it will be positive on the anode, and this will be negative. It won't conduct. It will only conduct during the negative cycle. That means I will charge this capacitor negative, positive. All right. And by doing that, I will control my current between my drain and my source. All right. And that will vary my gain. That's automatic gain control that's been applied there. All right. You with me? But you can go read through there, and you must know the operation of a JFET. Example 16.1. They say, determine the resonant frequency for the wing bridge oscillator in figure 16.12. Also calculate the setting of RF, assuming the internal drain source resistance, Rx and Ds, from the JFET is 500 ohms when the oscillations are stable. You also remember about Rx and Ds, all right? Electronics 2. Now they say solution for the lead lag circuit. R1 is equal to R2 is equal to R is equal to 10 kilo ohm. C1 is equal to C2 is equal to C is equal to 0,01 microfarad. The frequency is FR is 1 upon 2 pi RC, and that will give me a resonant frequency of 1,59 kilohertz. All right, that will be my resonant frequency. And then we must also calculate the setting of RF. Here's something I don't agree with. They say the closed loop gain must be 3 for the oscillations to be sustained. For an inverting amplifier, the gain expression is the same as for a non-inverting amplifier. Do you agree with that? Is the gain expression for an inverting amplifier the same as a non-inverting amplifier? All right, depending on what I try to say there. If I talk about gain, I will say it's output voltage divided by input voltage. But if they talk about the gain expression, I don't agree with that. I think ignore that. The gain for a non-inverting amplifier is RF over Rin plus 1. But now we can say Rin is going to be R3 plus Rx and ds, all right? And then I can go and work out RF. Then RF is equal to AV minus 1 and times R3 plus Rx and ds. When we work that out, we get a value of 3 kilo ohms, all right? You must remember those two resistors are going to be in series, all right? Because the JFET, between the drain and the source, there's going to be a certain resistance. But how does the JFET operate? If I vary the gate voltage, what happens? That resistance is going to change. Why? Because the depletion area can become smaller or larger, all right? Depending on the voltage on the gate. Any questions? Yes.
Sir, is that the closed loop gain, is it always going to be a constant 3 or can it be more?
For this, for the wing bridge oscillator, the closed loop gain should be equal to 1, not 3, equal to 1. But the attenuation of that lead lag circuit is 1/3, all right? That's why your gain of the amplifier should always be 3. 3 times a third will give me 1. All right. Yes. What? Rx and ds. Yeah, in that case you should. Yeah, that's only in that one with the JFET in. Only with a JFET. All right. Next one, the phase shift oscillator. All right. Here we got a phase shift oscillator. Now let's first go and have a look. What type of amplifier is this? That's the inverting amplifier. All right. Because where's my input? At my inverting input. All right, it's the inverting amplifier. What is the phase shift across the inverting amplifier? 180 degrees. All right, between the input and the output, there's 180 degrees. Here they tell us the attenuation for that circuit is 1 upon 29. All right, 1 upon 29. In the case of the wing bridge, it's 1 upon 3. All right, here's 1 upon 29. That means the gain of my amplifier should be what? 29. To make it 1, all right, to make the closed loop 1. Here they give us the formula for the resonant frequency, FR 1 upon 2 pi, the square root of 6, not the square root of 6 times RC. It's only the square root of 6 times R times C. You with me? That square root sign don't go across my R and my C values. Some students make mistakes. I don't want you to make mistakes, all right? Now, what is the minimum and maximum phase shift I can get with one RC circuit? What's the minimum and what is the maximum phase shift I can get with one RC circuit? All right, I'm going to ask you. I'm going to start asking. Yeah. What are you saying? Tell me what's the minimum. All right, it says 0. What are you saying?
The minimum,
Yeah.
0.
Huh?
I think the minimum is 0.
All right, the minimum is 0. What is the maximum?
180.
What?
90.
90. All right, we can get a phase shift from 0 to 90 degrees with one RC circuit. Now we have a look here. There's how many? 1, 2, 3 RC circuits. What is the maximum I can get with 3 RC circuits? I can get 270. 90 times 3 will give me 270 degrees. What is the minimum? 0. All right. But what do we actually need across here to get positive feedback? What should the phase shift be across this part to give me positive feedback? What?
It's 360.
Now I'm asking, listen to my question. What must I get across this part of the circuit to get positive feedback? You tell me across the amplifier there's 180. Now what do I need across that to get positive feedback? We need 180 because 180 times 180 will give me, plus 180 will give me 360 degrees. All right. That means across this RC circuit, I need 180. When I got 180 and there's 180 across my amplifier, I got positive feedback and the circuit will oscillate. All right. You can go from, let's say, 0 to 270, but I will only get positive feedback when there's 180 degrees across my RC circuit. All right, you with me? And there's the formula. And here's an example. They say determine the value of RF necessary for the circuit in figure 16.14 to operate as an oscillator. Determine the frequency of oscillations. All right. First of all, we know the attenuation is 1 upon 29. The closed loop gain of the amplifier should be 29. And that means I got my input resistance as 10K. That means I can go and work out RF. RF is going to be equal to 290 kilo ohms. All right. That will give me a gain of 29. 29 times 1 upon 29 will give me 1. All right. And now I must go and work out my resonant frequency. And when I work that out, I get a value of 6,5 kilohertz for my resonant frequency. All right. The 20 oscillator. All right, this basically forms what? That forms basically a band attenuation filter. All right, a band attenuation filter with my resonant frequency there. That means that part is a low-pass filter. This is a high-pass filter. Why they call it a T-type of filter? Because it's like a T. And the response of that will be a band attenuation filter with my resonant frequency. All right. They don't give you a lot of information. They just show you the 20 oscillator. All right. All right, that brings us to our LC oscillators. Now, the LC oscillators is basically a LC resonant circuit, all right? An LC resonant circuit connected to an amplifier, all right? Next time, that'll be Monday, we will talk about the LC oscillators, all right? That means now you've got time to do revision and prepare for your second test.